Hi everyone, welcome back. In this video, I want you to think like your computer's assembler. And if you remember, the assembler is taking your assembly language instruction or instructions and converting it to a binary machine language instruction that your computer's processor can understand and execute. Okay. And in a previous video, we looked at R-type instructions like add, similar to something like subtract. In this video, we're going to do something a little different. We're going to look at an I-type instruction. I stands for the word immediate. Immediate instructions have what is referred to as the immediate field, which looks something like this, where we have a part of the field is not a register, part of the instruction is not a register, but what's considered an immediate value. Okay, so here is our has an immediate value, and that's some information that is stored directly in the instruction, like directly in the code. It's not something that we're referencing a register where the information can be found by looking in the register and grabbing the value that's there. Okay, so in this, and we're not using MIPS, we are using our ARM assembly. Okay, when we do this, we are going to this is actually a different instruction that it operates differently when we have an immediate field, okay? And often this is written as like an ADDI instruction where we actually use the term add I for add immediate, okay? Where we have two registers and then the immediate field. Okay, so our simulator happens to write it like this, the example below, where it's still listed as add and then register, and then the immediate value, right? We'll see later on about how, really even in this video, how this is a different instruction, okay? And one of the reasons that I refer to as it's different than the R-type is we have this immediate field. And so in particular, the opcode is going to be different, all right? We're going to see that the opcode is different than a regular add instruction to get this to work, okay? Now this is going to make sense that it must be different because when we pull up our reference sheet here. Okay, let's take a look at this reference sheet. And one of the things that I want you to kind of be mindful of here, if we look at the first two, rows, in particular, look at this, or we look at them both down here. Okay, the first two rows. Notice that the add field, or the add instruction, is listed separately than the add immediate. Okay. One is an R-type, which we saw in the previous video, right? Now we're going to look at I-type. The add immediate is an I-type instruction, okay? So we're really concerned at this add immediate, right? This add immediate field. And notice one of the first things we want to do, right, if we're trying to convert an instruction to machine language, is to know what format type is it, okay? And so we see that it's the documentation is showing us that it's an I-type, okay? When we look at the I-type instruction, and I can get the same information by this is just a screenshot from the documentation, okay, is notice that it makes perfect sense when you think about it. Don't try to memorize this stuff. Just think through why this makes sense, right? It must be in a different instruction format than our add, right? Because the add instruction had three registers, right? We had a destination register and two sources, okay? Right, so when we were doing this in a previous video, we had an instruction that had, right, it had three registers, okay? If we're doing an add immediate, and I'm going to write it with the I here, right, it's only two registers, okay, and then we have an immediate field, okay? So we obviously need to store this information here. It's different, right? The information that we're storing to represent that instruction is different. Okay, and we could see that represented when we look down here at these core instruction formats. Right, we could see that it's represented that way. Okay, we've got two registers that we're storing. Okay, and we're storing the immediate field. Okay, we're storing the immediate field. Right, we could see how many bits are available. Right, what's listed there, it's called, we'll see why it's particularly referred to as ALU immediate later on when we actually look at how the processor is built. Okay, but the ALU immediate, right, or the immediate field has 12 bits, all right? So you can get a sense of how big the immediate, right? That's a restriction on how large this value can be, or thinking of 2's complement, how small it can be based on how many bits we have to work with, okay? All right, so we know it's an I-type. We know we've got these 4 different values that we need to figure out what they are. The opcode, right? We got our 2 register values, right? And then we have the immediate field, right? So if we're trying to encode this instruction in a machine language, right, we're going to have the opcode is defined by the opcode for an add immediate instruction, okay? And then we've got the immediate's pretty obvious that it's going to come from this 255 is going to be our immediate value, right? And then we have our RN and RD registers are these guys here, R0 and R1, okay? Right, those are the 4 pieces of information that represent that instruction. For the opcode, we look back at our documentation, right? The opcode is represented here in hex, okay? And the hex is telling us that it can be either 488 in hex or 489, right? Well, why could it be either one? Well, kind of, if we write it out, we can kind of see why that makes sense. Let's take 488, right, in hexadecimal, and let's write this in binary. Okay. Okay. Notice that's 12. Notice that that's 12 bits. Okay. And down here we don't have 12 bits to represent this instruction. It's less than that, right? We have 10 bits, right? We have 10 bits to represent. Okay, for the I-type. So we're going to lose some information, right? We're not going to represent all 12 bits here. Are not going to be able to be stored down into this field. Okay. One really handy way to make sure you don't make a mistake here, right, is we can look up even right in the back of the sheet. Makes it really, really simple. We look at the add immediate field a little bit here, right? We could see that it's going to be 488, 489 stored in terms of 10 bits, right? Is going to be 1, 0, 0, 1. Right, 0, 0, 0, 1, 0, 0. Okay, so we look back at this and say, well, how did that represent our 10 bits? And effectively, what we're doing is we are losing a bit in the beginning and the end. All right, those are the 10. These are our 10 bits. Okay. Okay. Those are the 10 bits that we're going to be representing. And so just confirm that everything was correct, right? This is 1001. Okay, 1001, 1001, followed by 3 zeros and a 1, 3 zeros and a 1, followed by 2 zeros. Okay. And that's correct, right? We go ahead and we do that, and it's correct. So this back page is a nice way of just double checking you didn't make a mistake. Okay, just to kind of recap here, right? We effectively lost, we used the hex, but we're only taking the kind of middle part here of that, right? And effectively why that's showing 488 or 489 is because we're losing this rightmost bit, it doesn't matter if it's a 1 or a 0. Okay, we're not going to use it anyway. Okay, so it's irrelevant. It really doesn't matter. So that's why it's written that way in the reference sheet. It's kind of indicating here that it doesn't make a difference. Okay, if you have a 1 or 0 there, you're not going to use that bit either way in storing it. So it doesn't matter. Okay. All right. So moving forward, we know the opcode now. We know the opcode. Right. We might as well just go ahead and do it. We know the immediate field too. Okay. We know the immediate field too. And we could figure this out pretty easily in terms of what 255 is, because if you know your power is a 2, right, we know that 256 is a power of 2, right? 128 is a power of 2, 32 is a power of 2. I'm skipping one. 64 is a power of 2, and 32 is a power of 2, right? This is 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, right? So 256 is 2 to the 8th, right? 1 minus that is it's gonna be all. So if we had if we start writing our bits here, right? We know that if we have 8 bits in a row, because we start at 2 to the 0 is 1, right? We know that 255 is going to be all ones, like for 8 in a row, okay? Okay, that's 255. Okay, you could do it out in a calculator just to confirm, right? If you do 256, it's going to be 1 followed by 8 zeros, right? Because it's 2 to the 8th. So we know that the immediate field's 12 bits, so we're gonna have a leading 4 bits here. Okay, that's our ALU immediate field. Okay. And to finalize this, and this takes practice, we'll do a number of these. Like this is the first one to see, and you can kind of watch the video multiple times to let it sink in what I'm doing. But we're gonna practice this, right? We need to do a few of these, you know, to kind of let it sink in about what the steps are, right? And we're going to have in the class where you write code to automate this process, literally build a little assembler. By the end of that process, you have a really good understanding of what assemblers are doing and how they work. So then when we go here and we look at this to figure out RN and RD, we really want to look at this documentation here to make sure that we're using things correctly. Notice that the RD register is the one that gets written to, right? It's the one that gets written to, where RN is the one that's being read. We can tell this by looking at the documentation, okay? The register being written to, RD, is R0, right? R0. So I'm going to put 5 zeros here because the register address for that register is all zeros, right? And then obviously R1 is going to be just 1. And then so we have here this is our final binary representation, right? We could switch that over and look at it in hex if we wanted to, but there we go is our final representation in binary. Okay, it might not be a bad idea to do it in hex just to kind of see it. It's a more concise way of representing this information. If I go over here, just so I can look at it and not make a mistake, I think the easiest way of writing it in hex is let's just make sure we get everything grouped by 4 bits so I can see things easily. Okay, I'm just writing it out where we're spacing things out by 4 bits. Okay. Okay, I think I did that right. All right, so that's in binary. If we do this in hex, we're going to have 9, right? 1, 0, 3. Okay, 15. 15 is F, right? This looks like that's 12. So 10 is A, right? 11 is B. 12 is C, right? 2, 0. Okay, so this is in hexadecimal. This would be our answer in hex. Okay. All right. Now we've covered R and I-type instructions. There are more. We're going to do some other stuff first before we look at D-type instructions or data transfer instructions, but we want to get some practice using those first so that we know what they are, which we haven't really seen yet up until this point. It has to do with using some memory in addition to using registers. So we will do more of looking at how to create the machine language to basically doing what the assembler is doing by hand. We will code it up as well and basically build a little mini assembler. But we will take a pause on doing this type of assembling, doing by hand, as we learn some other things, and then we will look at additional instruction format once we've covered some information that leads up to it. But that's for another time and another video.